right. Well, thank you for the introduction, and thank you all for coming here. Like I said, my name is Adrian Salai. I'm a PhD student here at Rice. And today I'll be talking about some of the work we've done, which uses multigrid methods, which are traditionally used for solving linear systems related to science and engineering problems, and using the principles of those to guide the design of deep neural networks, specifically for medical imaging segmentation. All right, so to just give a summary today, we'll talk about why we even did this to begin with. I'll talk about the similarity between these multigrid methods and convolutional neural networks. I'll go into some of the results we've used, what we've gotten from this, and then we'll conclude. All right, so why are we doing this? So if you've ever worked with convolutional neural networks, you know they tend to have a lot of parameters. They're large, they're expensive to train, and even for something like a classification task, you can have between 10 to 200 million parameters, depending on the architecture you use. So this large number of parameters can lead to the need for pretty expensive equipment, a lot of memory, a lot of GPUs that can handle this kind of data, and you can either buy your own equipment. In that case, there'll be a cost associated to it, or you can resort to cloud services, which come at an hourly cost. And then if you're dealing with medical imaging data, then there's the added concern of privacy. So, all right, given these large models and the cost and the memory and all the stuff that's associated with training them, we asked ourselves, can we reduce the time and memory required to actually train these models for medical imaging problems? And then if we achieve that, can we also preserve the accuracy you see in these current methods, or even maybe improve them? All right, so that leads us to multigrid methods and convolutional neural networks. So at a high level, a geometric multigrid method, or a GMM, is used to solve some kind of linear system of the form, right, AU equals F, where these variables AU and F are all related to each other via some kind of geometric grid. The thing that you really just need to remember for this is, right, these geometric multigrid methods rely on constructing a series of grids, like you see on the top right over there, to iteratively solve this problem. And now these methods have been around for a while. They're well understood. We know a lot about their convergence properties and so forth, right? So we know, again, just remember they rely on a series of grids, just like convolutional neural networks, right? Where you can start with an image that's a certain resolution, you downsample it, you create some features, and you go on in that pattern to solve whatever problem you're trying to achieve. All right, so that leads us to the first part, which is this pocket net approach. And one of the immediately observable differences you have between these GMMs and CNNs is, right, CNNs tend to double or expand the number of features as you go to lower and lower resolution levels. But in GMMs, right, that information that's lost by moving to coarser grids is already accounted for by the grids that are above that, or finer grids. And just by the way, this notion of doubling the number of channels in CNNs after you downsample has been around since the beginning, late 80s, early 90s, with the design and introduction of the earliest convolutional neural network. So given the similarity between these GMMs and CNNs, we want to ask ourselves, okay, if we stop doing this for these medical imaging tasks, what happens? Right, and visually what this looks like, you have on the left a schematic of your classic UNet architecture where, right, you start with some number of features at the highest level, you double until you reach your encoder at the bottom. But in our case, we decided, okay, let's stop doing that and explore the similarity between these GMMs and CNNs here. So in terms of the number of parameters, if you plot here on the x-axis, the number of parameters in millions versus the full and pocket versions of these several architectures that we try here, you see that you get parameter savings that are on the order of several orders of magnitude. Right, and so just as an aside to test all of this, we're going to be using the brain tumor segmentation data set, or BRATS. It's multiple channels, T1, T2, TC, and FLIR images, as well as tumor segmentations, which consist of multiple subcomponents. Right, so to answer the question, can we use this to reduce the time and memory required to train these models for 3D medical imaging segmentation? The answer is yes. Right, if we were to just use, say, a basic UNet and a 64-cube patch size in this case, you can see our peak memory usage on the left in terms of gigabytes versus several batch sizes. And in some cases, we have up to a 90% reduction in the number of parameters. As for training times, you can see here on the right, we'll plot the average time per training step versus, again, batch size. And we have, in this case, up to a 40% reduction in the number of parameters. This is just for a basic UNet. If you're familiar with the NN-UNet approach, it's kind of the latest, greatest state of the art. approach for these medical imaging tasks. You can see here that you also get some pretty substantial reductions in the training time required. If we go without automatic mixed precision, which again is a popular approach for time savings, you can see you save quite a bit of time in 5-fold cross-validation, and then again, you see a similar percentage-wise decrease in the amount of time required to train this if you go for automatic mixed precision. All right, so what about the accuracy? If you were to train all of these models, their pocket and their full approaches on, say, the BRATS data set here, you can compare, right, the distribution of the DICE scores. And you can see they're all pretty much identical here for the case of, say, the whole tumor segmentation, but it would be the same story for all of the subcomponents as well. All right, so that was the PocketNet approach. Now, you saw there that we pretty much match the full versions of these architectures. So what about using multigrid methods to, say, improve the segmentation accuracy? And that's what leads us to this full multigrid or FMG and WNet architecture. So within this multigrid framework of solving linear systems, right, you have different kinds of iterations, right? The most common being this V-cycle approach, which you see here in A. And this is actually very similar to the UNet architecture in the sense that you're going down to an appropriate resolution, going back up, and actually use some notion of skip connections, which they call corrections here. But there's other well-known cycles like the W cycle and the F or FMG cycle, which you see in panels B and C here on the left, which are actually known to have better convergence properties, which you can see illustrated here on the right. If you're trying to solve a linear system, you can see that these W and FMG cycles actually converge much faster. So our hypothesis was, okay, if we were to design neural networks based off these cycles, can we see faster convergence to lower loss values as well as an improvement in accuracy? And so, right, when we design these architectures, here's a sketch of the UNet versus what we're calling the FMGNet and WNet architectures for different depths or number of pooling operations you're using in your encoder. And here we'll illustrate it with the skip connections for the number of poolings or depth set to 3. Right, and so as for our hypothesis for the convergence, it's not very strong here in the training loss, where you'll see the UNet's loss values here on the top, and then our FMG and WNet loss values here on the bottom. But it is apparent here with the validation losses, where you can see we're achieving lower loss values faster or in less iterations than we see with your typical UNet architecture. All right, so what about accuracy? You'll see here, we're just going to plot this visually. Starting on the left, you have the ground truth, and then the FMGNet architecture, the UNet, and the WNet architecture. And you can see they're performing all about the same for these easier examples on the top. But as you go down towards the harder and harder examples, you'll see that the FMG and WNet architectures are producing, in this case, visually superior predictions to the standard UNet, which is right here. So I'll leave this up here for a second for you guys to take a look at. All right, so to conclude, right, we've seen here that we can use these multigrid methods to, A, reduce the number of parameters in existing architectures, as well as saving time and the time and memory required to actually train these architectures. And we can achieve similar performance in the case of the PocketNet versions of these architectures and better segmentation accuracy using the W and FMG nets, which we designed, versus these conventional CNN architectures. The Pocket Network is available on IEEE Transactions on Medical Imaging. The QR code on the left will take you to that. And then our FMG and WNet architectures are, or the paper at least, is available on archive as a preprint and is available on the right. Again, the QR code will take you there. I'll leave these up here for a second in case you're interested. Finally, we do make our code available here on GitHub. We actually developed a framework called the MIST framework, or Medical Imaging Segmentation Toolkit framework. It's fully automated. It can ingest an arbitrary data set and completely run a 5-fold cross-validation with pre-processing analysis, post-processing, everything. So again, I'll leave this up here for a second in case you're interested in it. And it's also available in TensorFlow and PyTorch as well, so you don't have to worry about not knowing to use which one or the other. And then finally, I'd like to thank my advisors, Dr. Beatrice Riviere here at Rice University and Dr. David Fuentes at MD Anderson, as well as my co-authors and collaborators. And again, I'd like to thank MD Anderson, Rice University, and the ND-Seg Fellowship for their support. That's all I have for you today. Pending any questions, that's all I got.
Thank you, Adrian.